team at Apple. He's going to give us an overview of the data flow graph IR and JavaScript.
Cool. Thanks, Fabio. I'm going to take the liberty also to sit. I'm feeling quite jet lagged today. Before we start, I guess it would be great for this to be somewhat interactive. I'm going to show a ton of pictures and walk through a bunch of like the semantics of our IR. Like, interrupt me at any moment in time to ask what's going on. Like, I think about this stuff every day. I understand it, but if you are confused about how something works, you're probably not the only person in the room. So JavaScript Core is the JavaScript VM backing the WebKit browser engine. So used by a lot of Apple products and used by Safari, but it's also used elsewhere. What were you telling me yesterday? It was used on a vacuum cleaner or something like that? I see. I see. Oh. I'm hoping, okay, a mixer. So I was very happy to hear that what we do ends up there. So what is JavaScript Core? So this is sort of a very high level overview of what our VM architecture is. So when we get JavaScript code that we have to execute, we first parse it to an AST. And from the AST, we generate bytecode. And our bytecode really lives on as the source of truth for a program for the entirety of its execution. And the bytecode is also what feeds into our 4 execution tiers. So on the left, we have an interpreter we call the LLint. And as you move from the left to the right, we essentially trade compile time for throughput. So as you move towards the right, every compilation takes longer, but executes faster and generates better code. So the interpreter and the baseline JIT are really bytecode first tiers. So they execute the bytecode directly, and they don't do any form of speculative optimization. The DFG and FTL both do speculative optimization. So we basically get profiling information from the program, from the JavaScript program at runtime. We take guesses about what the program does. If those guesses fail, we do something called OSR exit, and we move execution from those higher tiers back into either the baseline or the interpreter. So what do I want to talk about today? I'm going to go quickly over our bytecode IR, just because it sort of is the source of truth, as I was saying. So it helps to understand how the DFG works by first understanding our bytecode. Then I want to give an overview of our DFG IR, and basically sort of like from the perspective of how it supports speculation as sort of this foundational building block, and sort of the optimizations we can then build from speculation. And I'm gonna talk a little bit about how we implement speculation. So we do that via OSR exit. Then I'll talk about how speculation allows us to do type check elimination, common sub-expression elimination. And then if we have time, I'll talk a little bit about if you're hacking on JavaScript Core, like how could you think about implementing a new feature in our IR? Cool, so our bytecode is just a sequential list of instructions, and the semantics of those instructions are very high level. So if you have like an add instruction in our bytecode, it matches JavaScript semantics, which might do string concatenation, it might do property lookup and call to methods, it might add 2 integers together, it might add 2 doubles together. And our bytecode is essentially a register machine. So any given bytecode can read some registers and write some registers, depending on the semantics of that bytecode. So here's a big bytecode blob for this foo function. And foo is just a simple JavaScript function that takes in 2 arguments and adds them and returns them. So before we go through what this function is doing, let's just look at the single add instruction. So the first thing you see here on the left-hand side is just a bytecode index. This tells you where in the stream of instructions you are. Next, you have the opcode. And like I said here, this add really represents what an add in JavaScript does, which might do all kinds of crazy stuff. Next, you see the 3 operands to the add instruction. So here we use the left-hand side and right-hand side, and we write out the destination. And then we see what we call virtual registers, which are the actual values that those operands have. So here in our previous function, we're taking 2 argument virtual registers, and we're defining the local 6. So let's walk through what this program does, just to understand a little bit better how our bytecode works. So the first thing we do is the first 4 instructions here are really what we emit for the prologue of every function. So the enter bytecode just initializes certain locals to undefined. This is to support the JavaScript var semantics, which var is hoisted to the top of a function, and they all need to be initialized to undefined. So we do that just with 1 bytecode. Next, we have a get scope. If you look closely here, this is really just dead code, but we emit it at the prologue of every function, where we're getting the scope if we had to do closure variable access. And next, we just move that scope into another local 5. Then we have this check traps instruction. This is here to support runaway code, which is a feature we support to our API users in our VM. And then we get back to our add instruction, which stores its result in local 6, and then we return local 6 from the function. And of course, our bytecode can have control flow within it. So here you have a separate program, and you see that we have this J false opcode. So that's a quick overview just of how our bytecode works. Does anyone have questions? Yeah. Yeah, so virtual registers can be constants. I actually removed this slide. Maybe I should have kept it. Instead of arg2, you might have something like const 0. So virtual registers can be arguments, locals, or constants. Arguments are passed in, locals are defined by the function. Constants, I guess, are also defined by the function. Yeah. So you might have many scopes, and this local 5 in this case is just tracking the top level scope. So if you pushed a bunch of scopes on your stack, all of those pushes would have basically 2 locals associated with it. One that's that current scope, and then it always moves it into local 5, which represents the top of the scope. It's not special. There's nothing special about local 5 here, but it is something that the bytecode generator that takes the AST and produces bytecode will know that it has a designated register. Yeah, so the unfortunate thing here is we generate this code even if you do no scope operations, but our optimizing compiler kills it. Probably we could just kill it in bytecode very easily too. Yeah.
These instructions have this tag, these arguments have this tag, just left-hand side, right-hand side.
Yeah.
Why is this needed? Can we switch the depth and the left-hand side, for example?
There's nothing special there. This is just printing. We have a person who created the DSL right there, that we have a Ruby DSL to define our bytecodes, and we can give each operand to the bytecode like a name in English, so it's just easy when you read it. We used to refer to all of our bytecodes by specifically an index. So instead of seeing destination here, you would just see index 0 is the destination, and everywhere in the code that used index 0 would be implicitly the destination. So sort of, this is just for readability. Yeah, so everything I'm showing today is just the pretty printed versions of our IRs. Make sense somewhat? Cool. All right, so DFG. Like bytecode, it is quite a high level IR. We want to reason about the semantics from the JavaScript perspective. So if you have an add node in our DFG IR, it's also like our bytecode. It can handle int32s, it can handle doubles, it can handle objects, etc. And unlike reading and writing to registers, our DFG IR has both a control flow graph and a data flow graph. A control flow graph is just a list of nodes, and the program executes in the order that the nodes are listed per basic block. And a data flow graph means that each node can point to other nodes that it uses. And sort of the main thing that we do in the DFG is all of these speculative optimizations, and we implement that via OSR exit. We have 2 forms of our DFG graph, one which is called CPS form. This is actually, if we talk about just the DFG tier, this is the form of the IR it uses, and it's really aimed at compiling quickly and just doing basic block local optimizations. And then our FTL lowers the CPS form into SSA, and SSA works as SSA works anywhere else. And we really focus on doing global optimizations there. And that's the version of the IR I'm going to talk about today, just because it's a little bit less crazy. Continuation passing style in a very not super continuation passing style way. But the reason is each block kind of pushes its values to its successor block. That's what it's meant to stand for. In reality, we call it CPS and don't think too hard that it's not the CPS you know about. So our previous JavaScript function that took two arguments and added them together would look like this in the data flow graph. So your return node has a data flow edge to your add, which has a data flow edge to loading your two arguments from the stack. And of course, we also have the control flow graph, like I was saying. So here we have a list of nodes and you have the control flow edges between basic blocks, and each basic block has a list of nodes. So let's jump into like exactly what we're looking at when we look at one of these nodes. So the first thing you'll see is this number prefix with the @ sign. And this is just the node's identity. So it's just a way of describing what that node is. It's just a variable name. And then we have our node opcode. So like I was saying, this is really a add operation in JavaScript. And then this is where things get interesting, which is we have these inputs, which are node 10 and node 5. And we also have this demarcation of a type speculation. So this is something intrinsic built into the IR, which is you might have these data flow edges, and on every data flow edge, you might speculate on what type that incoming value is. So of course, that means we overload things like the add operation. So previously we were speculating int 32, but we might also speculate that the inputs are strings. So instead of doing an int add here, we would be doing a string concatenation. And here's a flag indicating if the node might exit, of course, because we're speculating this one can. And then this is also probably the most important bit of information here besides the speculation, which is what bytecode we come from. And if these speculations were to fail, what bytecode we would exit to. So here we would exit to the beginning of the add instruction. And then another flag saying if it's valid to exit. So of course, if you exit, then it must also be valid to exit, but you can be valid to exit and prove that you can't exit. And the operational semantics of a DFG node are first, and every node sort of has this pattern where you first execute your type speculations, and then you actually execute the node value itself. Take a second to pause here. Does this sort of make sense to people? All right.
Why are the type speculations not their own nodes? Why aren't they part of the value add?
They could be their own node, but it's sort of more cumbersome than you just have checks that you pass along everywhere in your IR. So you would end up with multiplicative number of nodes per data flow edges. It's also kind of nice to, like, from a perspective of like reasoning about the IR, it's sort of nice to know all of the modes that it can be in. And the way you check that is like, how am I speculating on my data flow edges? If you wanted to do what you're saying, you would emit checks for int 32s, right, on your add node. And then you would tell your add node, I'm like an int 32 add. But now we just do that by encoding the speculation information directly in the data flow edge. But it's not like a fundamental restriction of the IR. It's just sort of, here's how we construct it to make it really easy to do speculation. Yeah.
So where do these type speculations come from? Do you do some sort of type input first, or?
We do a lot of value profiling, and from that value profiling, it does flow into some amount of type inference. So if you have a load from the heap, that's where value profiling comes in, because you don't really know what it's going to load. But if you have an add, you can do type inference, because if the inputs are int 32 and the add never overflows, you know that you're going to produce also an int 32. So it's a combination, a little bit of both.
And how do you know how accurate these are?
Quite accurate. Yeah, I don't go into detail about this, but like in general, like the probability that you have to get your speculations right on average is like above 99%. Otherwise, you don't run quickly. Yeah.
Do you do polymorphic profiling yet?
Yes. Yeah. So we, like, for example, your add instruction might see double and int. In that case, we will speculate it's a number. We probably won't emit great code for something like int and string. We'll probably just emit our generic code for that case. But if you know that the inputs are int and string, as we'll see later, that information can be flown through like our type proving abstract interpreter that will know that the results would be only certain outcomes there. Like if you have int and string, then you can either only produce probably number because your int's add could overflow and you could produce a string.
And the node, if you have int and double, it just looks like you have the int speculation and then the exit goes to the double head and then that has the double speculation.
Sorry.
So if
yeah.
you say you have this, you have the value add node somewhere.
Yeah.
And you've seen ints and doubles.
Yeah.
And then
Yeah.
what does that look like? Does it
yeah. So that'll look like a.
First, and then there's an exit to the type speculation for double. Like,
no, in that case, we'll just speculate that it's a number.
okay. So
And
really have a generic.
a number case, but what we'll really do in practice is get everything into double format. Because the reason int format really helps you is when you flow into like array indexing and stuff, because you don't want to go between your int register file and your double register file or your floating point register file. And we degrade pretty quickly just into doing double arithmetic everywhere, just because it's faster than converting between double and int. So I guess the question is, why do we speculate? So I'm going to kind of go over some of these things later, but we'll talk about how speculation can allow us to do type check elimination and control flow flattening. And one of the main improvements to the compiler is it allows us to do much more precise effect and alias analysis. Like, you know that your add over integers is not going to do arbitrary effects, and that can really help some of the optimizations that we do. So sort of to motivate why we want to speculate, let's look at this do math function, which takes this argument and does two adds on it. Let's assume here in practice that our A argument is going to be a double. And if we emitted this code in our DFG IR without speculations, looks something like that. And if you kind of inspect the code you generate at runtime, you end up with these two double checks on your argument, and they're not redundant because the first double check might fail and go through the slow path. So you can't prove anything about what this argument node 37 was. And you also can't prove anything about what the resulting operation of the add is. It can produce any value. So if instead we speculated, we know that the second check is redundant with the first check. So we're allowed to remove it from the IR, and we can also, from the emitted machine code. And we can also know that the double add itself will produce a double, which then if that flows into other things, you know that the proven value of that operation is a double itself. So what exactly is this concept of OSR exiting? For us, it's sort of an implicit control flow where everywhere we exit, we have this implicit control flow to our bytecode tier. And this is what we call a sideways exit. So it's a one-way edge. You can't re-enter your optimizing tier when you take one of these speculative exits. And that's sort of important because you need to think about that as sort of, when you enter your bytecode, you obviously have maximal read and write effects, but the compiler mostly just reasons about the read effects because you can't really arbitrarily sync a store below an exit, because then if you did take that exit branch, you would no longer observe the store, and that's observable to user programs, but you don't really have to consider write effects because the writes are only happening when you exit. Yeah. Yes, yeah, you can re-enter later on, and that's sort of modeled differently. So for catch, for example, we model that as an entry point. So you don't reason about it as sort of a reentry. And for loops, we can also enter from loops, but it means that certain optimizations can't happen across loop boundaries because you need to assume that you're entering from a loop. Yeah. Yeah. Yes, yes, yeah. So OSR exiting doesn't prevent you from calling back into these optimizing tiers, but it does feed into the feedback loop of when you want to de-optimize the code. So OSR exit and de-optimizing the code are sort of two different things. The feedback loop is if I exit enough and what we call jettisoning, which is throwing away the code, then I'll go back to one of my bytecode tiers permanently until I get enough new profiling information and then tier up again to a new version of the DFG or FTO. Does that make sense? Okay. And one of the key invariants here is when we do an OSR exit from our speculative tier to our bytecode tier, the key invariant is we must reconstruct all of the live state from that bytecode and then rematerialize sort of the stack frame and then jump to the code. So I kind of want to go over an example of how we do OSR exit, just because I think it's pretty interesting to think about. So this is the program we're going to be looking at. An implementation detail of our bytecode is that our arguments are live always. The main reason for this is if you call a function in JavaScript, it can then read the arguments of its other parent's call frame, as we were talking about. But the interesting variable to track here is the B variable, which we store in local 6. So we can see that this let B is essentially assigning undefined to B. It then flows into these two function calls, which then store the result of the function calls to B, and then we add B to one of our other arguments. And the high level of how we implement this is we have these metadata nodes in our IR that associate a given node with a bytecode register. So here we have all these move hints. And the way we reconstruct the state for OSR exit is we know what the live values are, and we can't remove anything from our graph that would then flow into a live value in bytecode if we exited. And the way we determine every live value in the IR to reconstruct the state that we OSR exit to is basically this forward pass abstract interpreter that as it's going, it's associating DFG nodes with bytecode nodes. Oh, sorry, with bytecode registers. So let's walk through how we would do that for this program. So we initialize our state to basically say that our two arguments come into the function on the stack and that our bytecode local 6, our B variable is initialized to nothing. We don't yet have a value for it. And the interesting thing happens when we execute our mov hint node. So this is going to take that undefined constant. So this is the let B at the top of the function and associate it with local 6. So now we get to update local 6 with node 23. And we see here that if we were to OSR exit on this Boolean speculation, that the main invariant is upheld, which is that we have values for all of our live bytecode registers. So here we have the two values on the stack for arg1 and arg2, and we have local 6, which is in the node 23. And then if we trace through one of these, one of the branches of the control flow diamond, we see the very same thing. So here we're assigning the result of the function call also again to our local 6. And we now update our map to say local 6 is represented by node 41, which was the function call. And then if we were to OSR exit at this int32 check, again, all of our live state is accounted for. And then to handle control flow merges, and we basically just rely on SSA here. So if you have like a normal SSA variable, you have to then update that in using a mov hint. So here our phi, which is node 19 represents local 6. And of course, then we have to mov hint that phi to local 6. And again, if we were to OSR exit here, all of our live state is accounted for. Yeah.
Like every exit has stuff, right?
Yeah, 2 answers. So in the FTL, it's not the most efficient storage. We actually have a stack map like this that we keep at every exit site. The main optimization we do there is we prune everything in the map by liveness, because all you care about are things that are live in bytecode. So that greatly reduces the size, but it's not the most efficient encoding. The DFG is a completely different answer. So this is the FT. So this is, to be clear, like how the FTL does it. In the DFG, the invariant is that your entire live state is spilled between basic blocks, and all you do is encode where your values are, either in registers or on the stack. And an OSR exit is just an index into this log. And the only information you have for an OSR exit is that index. And then if you need to reconstruct your values, what you do is you go to the last place, what we call a reset, which happens at the beginning of every basic block boundary. And then you walk forward to the index you are, replaying the log. And then from that log, you have an encoding of this, for example, local 6 might be in RAX or something like that. Does that make sense? Okay. Cool. So any other questions, I guess, on how we do OSR exit? All right. So the next thing I really want to talk about is how we do type check elimination. And we have a pass over DFG, both CPS and SSA, called what we call the abstract interpreter, which is kind of an absurd name. But it handles a lot of our heavy lifting optimization. So we do a lot of constant folding and constant propagation, and also effect modeling that sort of drives those analyses. So our abstract interpreter will keep track of an abstract value per value producing node in the IR. And the abstract value can represent these 4 things. So you might be a constant, and that's sort of the part of it that will drive constant folding. We also keep track of what we call structure and array mode. These are notions of type that can be mutated by the executing program. So structure is sort of like V8's hidden class or something like that, or shape in your VM. So if you do a function call, you might mutate someone's structure. And then we also keep track of this speculated type field. This is a notion of type that is immutable. So this might tell you if you're an int32 or a double, and no effect that happens in the program can change that something is an int32. So we're going to be kind of walking through an example of how this allows us to do type check elimination by using this abstract interpreter to drive the runtime code we emit. And there's a mapping from all of these speculation edges to a set of speculated types that are allowed to filter through. So if you have a Boolean edge, only Booleans are allowed to flow through, but you might have a cell edge, type speculation edge, which allows many possible things to flow through, but it's guaranteed not to be a primitive. Sorry, not a JavaScript primitive, but a non-heap allocated object. So I want to walk through how our abstract interpreter works at a high level. And the main goal just for removing type check elimination on these edges is to analyze each edge and to mark it with a bit that says this type check is proved or this type check is not proved. So we initialize our abstract state to be bottom. We don't have any values defined yet. And then when we execute this call node, we don't know what's returned from a call. So we have to initialize it to top. Mov hint doesn't change anything. And then again, the second call, the same thing. We don't know anything about what its type might be. And here's where things get interesting. So we have this Boolean check on the result of the second call. And of course, this call is top, right? We don't know it. So this check is going to have to emit a runtime check. That's what this check colon here means. But from this point onwards, in the rest of the abstract state, we know that this 10 node will be a Boolean. And then this state is passed along to the two edges of the control flow diamond. So if we walk through both of them, the left-hand edge is going to check the first function call in the program for it being an int32. And again, because it's top, we're going to have to emit a runtime check there again. And on the right-hand control flow edge, we're going to check that the first call is a double, and we're going to have to emit a runtime check there too. But things get interesting where we merge. So this control flow merge is just going to be a union over the types that were from each of the predecessors in the control flow block. So now we know that node 15 is an int32 or a double. And what that allows us to do in this value add node is analyze this first number check. And of course, an int32 or a double is a number. So we can mark this edge as proven. And then of course, the constant is also known to be, in this case, an int32. So it's also marked as a proven node. So we now are able to classify each of these speculations with whether or not they'll need a dynamic check at runtime to satisfy the type proof. I think you're. For 44, you know that an int32 is a number. Yeah, so number is how we're emitting this value add node, which is doing an add over numbers. And a number here just means int32 or double. It's agnostic to how it's boxed. Yeah. We do in a different abstract interpreter. Yeah. It is not, that's why I was saying it's kind of, so basically everything in our compiler is an abstract interpreter, which I think is the absurdity of the name, the abstract interpreter, but hence the.
Who would make the code that turns the input into? You said if you're doing some numbers.
Yeah. So, right. Yeah. So I'm kind of actually simplifying this IR a little bit. So in the DFG, we have three like sort of core value representations. One is you're an unboxed double. One is something called int52, which is like a kind of a JavaScript hack to allow big integers that fit within double format. And then the last thing is box JS value, which is the majority of things. We have these value rep nodes that allow you to take in something that's not a JS value and produce something boxed as JS value. And then we also have these nodes called double rep or int52 rep. And those are the nodes that will actually speculate that the thing is a double and then produce an actual double value that's not boxed. And I guess the interesting thing here too, of course, is that this add, now that its inputs are numbers, it also produces a number. So if this flowed into other data flow edges, we would not need to check that it's a number again. Yeah. We would, in this program, we would convert this constant to be a double constant, and then we would insert the double rep right before the value add over node 15. So what would really flow through here is a double rep over 15. And that would speculate that it's a number. Yeah. Yeah. Could be made slightly better. All right. That's sort of how we do type check elimination. Kind of want to jump into how we do common sub-expression elimination, but do folks have questions on the previous pass? Okay, so we have this helper, I guess, in our IR called clobberize. And its main purpose is to essentially categorize the effects of any given node taken with how it's speculating. So it can tell you where you read, write, like what abstract heaps you read and write, and then also if you define any value. And the key thing to sort of understand here is because we speculate, we're able to actually have somewhat precise definitions of these abstract heaps. If we didn't speculate, like every add, every arithmetic operation would blow away any notion of your heap, because those operations are fully effectful. So here's sort of a visual description of how we might break things into different abstract heaps. So if you have a program in a loop that reads the named property X, but the rest of the loop might write only to the stack, of course, you can hoist that property access to the variable X out of your loop. And this is the kind of information that our clobberized pass allows us to encode within the IR. So what does this look like in our C++ code base? So here we're looking at a bit not operation. And if we're have the untyped speculation, so if we're not speculating, this is a fully effectful operation in JavaScript, and we say that this is sort of the equivalent of being maximally effectful. The interesting thing here is the reason we say read world is, of course, anything in JavaScript can read the stack frame, as we talked about earlier, but you could not write to the stack frame from other function calls, so you only write to the heap. And then the interesting bit is, if you're speculating that the input to your bit not is an int32, we essentially define this as a pure value, which is not dependent on any abstract heap. And here are nodes for loading and storing closure variables. So these are things that we store in like a scope object. And the interesting bit is your get closure variable will read what we call the abstract heap for scope properties. And this scope offset is really a way of encoding the name of the variable you're reading. And for put closure var, we say that we write to that abstract heap. And the cool bit of information is that both of these will actually define the value at that abstract heap. So for get closure var, we're saying that the abstract heap scope properties and the variable X, given the scope node that's represented by the data flow edge child1, will produce the value node. And for put closure var, of course, it's not a value producing node in the IR, but we know what we're writing into the scope. So in that case, we say that child2, which is the value being stored, is what we define. So I want to walk through how we can use that information to do some basic common sub-expression elimination. So the first thing we're doing here is essentially mapping values to what we call a value key. And the goal is, as we encounter operations that define some value key, we first see if that exists in our map. If it exists in our map, we can then replace the node with an identity over the other thing that had the value key. So it'll allow us to remove redundant operations. Does that seem sensible? All right, so the first thing we do is execute this get stack node. So we update our mapping to say the stack location for arg3 is now represented by the value produced by node 30. And the next thing is this bit not, which is what we looked at earlier. And we mark this as a pure operation. So we're saying if we do a bit not over node 30 as input, we produce node 20. And next we have this get scope operation, which is similar to the bytecode we saw earlier. And this is a pure operation just because the scope of the scope object that we load is never is immutable. So we get to mark it as pure. And then we have this get closure var, which is loading the X variable from the scope. And here we now define this value key that says if we loaded X off the scope 10, its value will be produced in node 15. And then we now encounter this call operation. And if we saw the previous untyped use of arithmetic bit not, it's the same effects as a call might have. So it can read the entire world, but it only writes to the heap. So it's not going to overwrite this stack value, but it will overwrite this closure var because you might call a function that assigns to your X variable. So now we can no longer say that node 15 represents loading this closure variable from the scope 10 and variable X. But now we execute a store to our scope object, and this will say that with scope 10 and variable X, I'm storing whatever is produced by value 12, which is the function call, into that scope object. And next we have this bit not again, and what we see here is that we've already computed this value, so we can see that we have this bit not in our map already. And because of that, we can mark it as an identity. So we've essentially removed the redundant bit not computation. And next, we can also see that with loading variable X from scope 10 is already in our map. That heap location is in our map and is represented by the node 12. And what we can do here is replace this get closure var with an identity over the value producing node 12. So that's sort of how we use speculation to help drive this analysis, because we can speculate on certain operations that will allow us to have sort of precise heap, will prevent us from clobbering precise heap locations. Because if we didn't speculate on this bit not, it would clobber the heap location produced by running node 18. So that's kind of how we do CSE. Do folks have questions on that?
What kind of data structure do you use to do this mapping from value keys to nodes? Like a hash map, or is it just?
Yeah.
So how do you handle the fact that you are adding, that you're unifying stuff, right?
Yeah.
So
yeah, so we probably don't do like awesome GVN. We do very simple unification. So like if you produce the same value along two edges, we don't even do CSE in that case, because we won't insert like the necessary phi variable to represent that. But if you produce something in a block that dominates two checks, two opposite blocks that don't invalidate that heap, if you have a join point, you will still have the same value produced in the heap in your dominator.
construct a mean example, but I'll do that later.
Okay. Yeah.
Why is it at 12 and not 8:15? If you go back one step, it will show me the exact line in 15, right? I didn't understand why you can optimize away the call.
Why you can optimize what?
The call in 12, right? You're replacing it with 12.
Oh, so line 18 is storing the result of the call
Yes.
into the scope 10 with the variable X.
Oh, right. Oh, sorry.
So that's like scope.x equals 12. Yeah. So here we can see that what's in the scope is the result of the function call.
It just happens to be exactly the same call. You overridden the value of X.
Right.
Okay.
Yeah. Okay. So kind of wanted to jump in for this last part of the talk of just like how, if you're like working on JavaScript core, how might you think about adding IR to how you would add the IR for representing these basic hash map operations. So in JavaScript, we have this map object. It's a hash table. It has three functions: has, get, set. It has a few more, but that's all we really care about for this. So how might we go about like designing an IR that can take advantage of some of the optimizations we saw in previous parts of the talk? So here's kind of the function I'm targeting for the main driver of this optimizability of these nodes. So here we're asking if a hash map has a key. If it has a key, we return getting that key from the hash map. So sort of, if you consider this from like the basic set of operations that you'll do in a hash table, this will result in hashing your key twice and doing hash table lookup twice. And this is really all the API that JavaScript offers. Like you can't do better than this from the current APIs that are defined by the language. So I think the starting point might be just developing trivial nodes for both has and get. And if we look at our previous example, it does buy us some amount of optimizability, right? So here we know that if you have a map has node in your IR, it returns a Boolean. Therefore, the branch isn't going to have to check if the result is a Boolean. That's a proven value. And if we get the value from the map using the map get node, that second type check is dominated by the first type check. So we already know that the input's going to be a map. So we omit a secondary type check there. But if we think about sort of hash table, the characteristics of a hash table, we are not considering a lot of redundant operations. For example, hashing the actual key that you take into your hash map. So another potential design approach is to, instead of passing in just a key, you also pass in the hash value of that key. So if we look at that same program with this new IR design, we get the same benefits as before. We remove that Boolean check at runtime. We also remove the second redundant map check. But we also have these two hash nodes, and these hash nodes, the second one is redundant with the first one. So here we save a good amount of work hashing the key twice. But I think we can do even better than that. So the main thing we're missing out on is that we're still doing two hash table lookups, and hash table lookups fundamentally are just expensive. So what if we taught the IR about what it means to do a hash table lookup? So here, we're adding the ability to load a hash table bucket, and the operation for has is asking, is that bucket some Sentinel empty bucket, which represents the key not being in the map? And then get will be similar. We're going to load the hash table bucket, but then we're going to load the value from the hash table bucket. So if we look at that same example program, we get all of the same optimizations as we did before. We get these two type checks, which are proven, so we don't have to omit them. We get to remove the redundancy of hashing our key twice. But the best improvement we get here is we actually remove the second hash table load. And this is what we actually implement today in the DFG. Yeah. No. Yeah. That's why we can remove. Yeah, no, it's side effect free, which is why it's so enticing to move into its own node. Otherwise, what I did here wouldn't work out. I think that's all I have.
We still have plenty of time for questions, if you have any.
Yeah.
For the beginning.
Yeah.
So how important is for your workload to have the performance? One couple of examples for something that looks relatively trivial.
Yeah. The biggest optimization we do is probably inline caching and having fast paths. So like for the add, which is a polymorphic operation in JavaScript, we have like inline assembly fast paths for adding integers, adding doubles, stuff like that. For property access, we do inline caching. Those are probably the two biggest optimizations we do. We don't do a ton of analysis on the bytecode itself to improve the speed of it. To answer your question, your first part of the question is interpreter performance is super important. Yeah. So we do some other interesting things. So if there's sort of two use cases. One is you're running in a JITted context and one you're not running in a JITted context. The latter we really need to do better at, because specifically for us, it means like every iPhone app that isn't privileged to run the JIT, which is every third-party app, only gets the interpreter. So we want to implement some optimizations to our inline caching that will make that use case a lot better, that's probably where we would get a lot of performance that we're leaving on the table. So stuff like polymorphic inline caches. In the JITted case, what we want to do is start sharing some of our inline caches from the interpreter with the JIT. And we now do that for calls, but we don't do that for our property inline caches. I see. Yeah, we don't do any eager allocation of inline cache space. Yeah. So, I mean, I guess I've not had to evaluate that world, but it makes sense. Yeah, it's also probably run once code you don't want an inline cache for either. Yeah.
What kind of profiles do you collect? Do you just collect, do you also collect certain properties for certain operations like
yeah. Yeah, so a lot of what I talked about today is what we call like value profiling. That will be type-based profiling. So it gives us that speculated type thing, this immutable version of type that we talk about. We collect a lot of other profiling, specifically like what shape are you, stuff like that. And that's encoded in our inline caches. So we use inline caches both as a runtime optimization, but also as a method of providing profiling to the upper tiers. So let me give you a specific example. You overload from one shape, the property X, right? And the inline cache is going to tell you this information. So what you do when we generate DFG IR from that is we'll look at that inline cache that we generated, see that we only ever have one shape, emit this thing we call a structure check, and then load that value directly.
My question was more not about shapes, but like properties of integers and things like that, right?
Yeah, so I was talking to Carl about this yesterday. So we used to infer types of properties, and that was actually turned out, we got a speed up when we removed that mechanism. We could obviously write micro benchmarks and stuff that got faster, but one of the benchmarks we care most about was like 1.5% faster when we removed that capability. But we do have something very similar for arrays. So for our arrays, we'll profile if they're like int32 or double, stuff like that. And that's like actually something encoded in our type information for arrays. So you know if you're loading from an int32 array that you're only ever going to get an int32. Same thing for double arrays.
But for really expensive operations, like they also do operation specific profiling. You know, for certain bytecodes, do you do any of that, or it's always?
We definitely do some operation specific profiling. For example, for calls, we also take an array profile because you might be doing some kind of an array operation. So when we go to inline the call, either to what we call like an intrinsic, which is the map stuff I was talking about, we want specific to the call, what did this see? For add, we don't do value profiling, but we do profiling on what the result is. So we know if like an add overflows is another example of like a bytecode specific profile. Yeah.
I remember you asked a question this morning to Max, and I was hoping you would return, so I do it. So if I change something, right, how do I measure the performance impact? Can you shed some light on that?
Yeah, so the WebKit team at Apple has like a performance infrastructure that we use. So if you're working on a patch, we have the ability to submit that patch to do performance testing on, and anything you can do on that bot, you can also run locally at your machine. So typically we will compare both with and without a patch and then do some statistics to see if we think it's a significant improvement. As a rule of thumb, you don't check in anything that makes the code slower. If so, it gets rolled out. If you have something that makes a micro benchmark faster, but doesn't make anything else slower, that's like fair game to check in.
And who decides what gets into your benchmark suite or not?
We do. Yeah. Yeah.
In my guess, so you have several JIT code from the IR.
Yeah.
So how many tires does JavaScript core have?
Yeah, so there's 4 tiers. our DFG tier, we go directly. So, okay, so for our interpreter, we interpret our bytecode directly. We then have, I guess, what you would just call like a template JIT, which is our baseline JIT, which is, it does some amount of profile specific code generation, but very minimally. And basically it spits out the same code, just removes interpreter dispatch overhead, and it has a better form of inline caching. Then we have our DFG tier, which is the IR I talked about today, but it's also the faster version compiling of our IR. So if we go straight from this DFG tier to machine code. And then our FTL tier does a lot of optimizations after the DFG IR. So we lower to something called B3, which is very similar to LLVM. And then from B3, we lower to, so B3 is a SSA based IR, very like similar, has data flow edges, has a control flow graph. And from that, we lower to an IR we called AIR, which is assembly IR. And we do, that's not SSA based, it's register based. And I guess I said lower, but really B3 is sort of lower than your machine level instructions. And then you lift to AIR by doing instruction selection. And then you run register allocation on top of AIR. And then from that, you generate machine code. Yeah. Rediscover.
Where do you inline?
In when we parse bytecode. So when you parse a call instruction or another node that might be a call. So like stuff I didn't talk about, like loading a property might be a getter call. We have sort of things in our bytecode called checkpoints where you might be like 8 things in one bytecode that might do property access, might do function calls. All of those keep around profiling information. So the inline caches for the call. And then from that inline cache, we know if it might be something we might want to inline. And then we just inline directly from the bytecode of that function to DFG IR as we're producing the initial IR. There have been some thoughts about like, should we do inlining later, but it's not something we've explored. Yeah.
How do you store the metadata how do you keep around which inline thing you're
Yeah. So I simplified that part where I just said you're a specific bytecode index, but really what we store is the pair of what we call inline call frame and bytecode index. So you know how deep you are in your inline stack and at what bytecode you are at the top of that inline stack. So when we actually exit, what is the code we write to reproduce the stack frame? It is, but it's sort of very uninteresting. Our baseline JIT, if we're exiting to that, keeps a map of every bytecode to machine address. So if you have like foo calls bar and you exit in bar's frame, you have to, its return address needs to be foo. So you have to like write code to do that. And like the callee saves that foo uses are in bar's frame, stuff like that. So you're generating a lot of machine code that does stack frame regeneration. And if you're exiting to your interpreter, you just know what those code locations are, but you do the same kind of thing. Yeah. Yeah, so this is a really interesting question. We try to be as specific as we can in our optimizations to not overgeneralize until it's proven through some amount of information that it would be useful. So like, let's say you have a program that encounters some phase shift. So you have an add, it takes a bunch of ints, you optimize, and then it starts taking ints and doubles. In that case, we first generate the int32 add. When you start passing in doubles, you're going to exit. Once you exit like 100 times for the first time, we'll throw away the code, rediscover that it used doubles, and then regenerate the add to be polymorphic over int and double. But yeah, when writing speculation, our approach is to be as specific as possible, because if you generate worse code from the start, you're sort of permanently pessimizing the throughput of that code. Yeah.
I have time for one more
Yeah.
Hi, so when do you decide to go to the baseline JIT and the baseline JIT profiling?
Yeah, so the interpreter and baseline JIT both do profiling. And also the DFG does profiling for the FTL via inline caches. And if you exit from either of those tiers, you get profiling in that case.
You all
You-
share the same profiling or it's separate things?
It depends. So inline caches will not be shared. Value profiling or type profiling will be shared. And inline caches will also be like specific to your inline call like context. So if you're going from your DFG to your FTL, you might have a polymorphic inline cache that has like 8 properties, but in one inline context, you're only one property, in which case when you compile it in FTL, in one instance, you'll get the 7 things, in the other instance, you'll get just the one thing. We go from the interpreter to our baseline JIT very aggressively. I think something on the order of like 10 function calls or 100 back edges in a loop from baseline to DFG, multiply everything by 10, and then from DFG to FTL, multiply everything by 10 again as a starting point. There's some heuristic for like what the size of your function is, stuff like that, but yeah.
Well, let's thank the speaker again. Concludes ICOOOLPS, right?
Yeah, I think we're part of we're going to share the last.
Yeah.
And the last session is going to be in here, so we don't have to change rooms again.
And in case you have to leave now, but once you come back later, we are still planning on going to the
Oh, yeah.
micro